describe what it is. So logarithms, you can think of them as two ways. One is that they are specifically the inverse of the exponential function. So let's talk about this for a second. So if I have number a that's not 0, and it can't be 1 also, so let's get rid of those two cases, and I have a function, f of x equals a to the x, a nice exponential function, then it's either decreasing or increasing. We've seen this before. You have exponential growth or exponential decay, so either increasing or decreasing. In particular, right, the graph is 1 to 1. Therefore, it's 1 to 1 by the horizontal line test. If I'm 1 to 1, I have an inverse function. Therefore, there is an inverse function to my exponential, and this is what we call a logarithm. So this is what they're called logarithmic functions. Logarithmic, L-O-G-A-R-I, I can't spell. Logarithmic functions. We'll edit that out in post. Okay, called logarithmic functions with a base a. So you can have lots of bases. The one's going to come up in most courses is the natural log. And we denote these functions, and we call it f of x or f inverse of x, depends on what sort of what perspective you're taking. You put a little base down here, the subscript, and there's x. Don't get hung up on the fact that the base is called the letter a. Sometimes they put b in there for base if you want. X is also a dummy variable. That could be theta or anything else you want. But these are logarithms. They're inverses of exponential functions, and therefore they have a nice little rule here. So if I have the logarithm of a of x is some value y, that is only true if and only if the base to the output of the logarithm is the input. A of x is y. We'll do more of these with specific numbers, and you can actually see how they interact with each other. Okay, so let's move on. There's our definition. As always, if it gets to, I find most of the time when you see a definition, it's so abstract that it's a little confusing. Put it down, take note of it, and then always go to specific examples. So let's jump right to that. So as an example, let's just pick a specific one. Log base 2 of x. Okay, so think about this. If this is the inverse to f of x equals 2 to the x. So whenever 2 to the x does the function, log base 2 will undo it. So 2 to the x, let's see if we can do this without having to rely on the exponential function. 2 to the x is exponential growth, goes from low to high, everybody's happy. We know that the graphs of these things are reflections about the line y equals x. So let's think for a second what's going on here. This graph would have to be sort of like this. If it's going to be a mirror image, if I tilt my head 45 degrees of this way. So what are some special points here? What's going on here? Where is this thing equal to 0? So let's clear on this for a second. Log 2 of x is equal to 0. Where is that true? That's true where 2, so take the base, raised to the 0 would equal x. So I can tell you exactly what the x value is, where this thing crosses the x to the 0, we all know that. That is 1. So this crosses the x-axis. Its x-intercept is exactly 1. That's true for actually any log base, and we can put this one as a general rule. So if I have log base b as a function that inputs 1, that's always going to be 0. And the reason is because the base to the 0 power is always 1. So that's nice. It's a graph. Let's talk about it for a minute in terms of the standard things we asked about graph. What's its domain? So its domain is, it's not all reals. Be careful, you can't plug in negatives here. If you look at the x-axis, the x values, you get 0 to infinity. I am using a parentheses around 0 because you cannot include 0. What is its range? Its range is a set of y values, a set of outputs. It goes down to infinity forever, goes up to infinity forever, so its range is all reals. We have its graph. And the asymptotes, we have a vertical asymptote. Vertical asymptote is like the y-axis here. This thing will get close, but it will never touch, and that's at the line x equals 0. Has no other asymptotes there. So describe this graph. It goes off to infinity, has nice end behavior. Just things to know about logarithm. The fact that we use 2, you pick any number greater than 1. This is just a specific one that we picked. Next, moving on. The fact that we use 2, you pick any number greater than 1. This is just a specific one that we picked. Next, moving on. Log rules. So let's try to put this in a different setting. You've probably seen these in some way before. So let's do log rules. So let's put down the one you've probably seen. So if I do log to a of a product is log a of x plus log a of y. So logarithms turn multiplication into addition. There's a bunch more of these. We'll write them down in a second. But let's just talk about this for a second. Here's the other way to think about logarithms. Logarithms are an exponent. When you put an exponential function, the variable moves upstairs. So if you think about logarithms as living upstairs in the exponent, so much so that I don't even write the base, but just know we're upstairs in the attic, then this would make more sense. So well, why does that make more sense? I don't really understand. If I have, let's switch over to a little bit non-logs for a second. If I have a base, so like a to the x plus y, and I ask you to do some algebra with this, what do you do with this? This becomes a to the x times a to the y. So when I live upstairs, which means logarithms, products become addition. It's a little weird to see, but that's exactly what's happening. You're working upstairs. Same thing with division. So let's do log base a, x over y. This is log base a of x minus log base a of y. When you're working with logarithms, division becomes subtraction. Is that normal? Why would that happen? Well, if you take the other side of the coin and look at division of exponential functions, how do you algebraically simplify this? This becomes 1 base x minus y. Division becomes subtraction in the exponent. A logarithm is an exponent. You're working upstairs. One more thing you've seen all the time with logarithms is that they say exponents fall out in front. So let's do something like this. If I have log to some base a, x to the r, then the r falls out in front, and it's r times the logarithm. So let's say, why would that be true? Well, if I take a base, and I have lots of them, so let's say do this many times, a to the x, what's going on over here? Well, this is a x, there's like r of these things, let's say. So it's r to the power. This is a to the x to the r. You're multiplying these together. So I have like a power, repeated addition, repeated multiplication. They get multiplied together, and you get a to the xr. In the exponent, raising a power to a power becomes a product. That's exactly what's happening here. Raising something to a power, maybe you don't even need this. For instance, a to the x to the r raised to a power is a product. That's exactly what's happening in rule number 3. This is not really a rule, but I'm going to put it in here anyway, so I put a little star next to it. Not a rule, but it might as well be. This is something that comes up so much, you might as well just treat it as such. If I plug in 1, you will always get 0 no matter what your base is. We saw this before from the graph. This comes from the fact that if I have an exponential function and I raise it to the 0 power, I'll always get 1. And this is just a common mistake that people make. If you plug in 0, think of the graph for a minute. So like, what is the log of 0 for any base? This is undefined. Some people will get confused and be like, it's 1. And like, no. So don't tell me that. It's undefined. Okay, so I put these little 2 down here. This is a simple thing to review. To play around with logarithms, let's do a quick example just to get some experience. If I ask you, without a calculator, without running over the thing, let's do log base 5 of 125. So log base 5 is a function.